Ladies and gentlemen, it is my privilege to introduce our esteemed speaker, Mr. Chad Watson, an accomplished data scientist and Bayesian statistician. With over 15 years of experience, our speaker has been instrumental in executing projects across diverse domains such as finance, risk, and medical statistics. Our speaker's strong quantitative background is complemented by an expertise in statistical and data modeling, as well as machine learning. This unique blend of skills has enabled our speaker to make significant contributions to the field and drive innovation. Please join me in extending a warm welcome to our distinguished speaker, Mr. Chad Watson.
Hi, good morning or good afternoon, depending on where you're from, I suppose. But I suppose everyone is morning or maybe early afternoon. Okay, so my talk today is actually looking at Laplacian approximation. So let me share my slide. Okay, share screen. Share. Is everyone seeing my screen?
Yes, now it is visible.
Okay, so let's now from the beginning. All right, so my presentation, everyone seeing that? Yes?
Yes, it's visible.
Yes, yes.
Okay, awesome. Let me just minimize this. Okay, so my talk today is actually using Laplacian approximation to calculate oil in place. Okay, so I promised it would not be maths, although the topic is very mathematical. The idea behind this is trying to look at small and medium-sized enterprises that may not be able to employ some of the expensive technologies that they use to make some of these calculations. So in this presentation, I would probably start off, not probably, I will start off with how to calculate oil in place, what current techniques that they use in terms of estimating this, common applications, the distributions that we normally use when it comes to petroleum risk. I would then look at the issues with SMEs. The reason why I'm looking at this topic, and now Laplacian approximation is actually a way of finding the maximum expectation for the mean distribution for using a posterior distribution. Now that's a Bayesian framework. It's technically not a Bayesian framework we're looking at, but because we're looking at expectation, and in petroleum risk, we sometimes use what's known as pseudo-MCMC algorithms, and you would have heard MCMC algorithms before. It's usually relates to posterior, but the reason why it's called pseudo is because you technically don't have an expectation, so to speak of. And then I would look at the Laplacian approximation and giving you a little insight on how it's calculated. And we would do a comparison between what we have from a reservoir simulation and the Laplacian approximation. So I know it sounds quite maths, but I promise you I would put very few formulas and it should be easy to follow. All right. I say that and you have an equation. So this is basically the formula that they tend to use to calculate the oil in place. So stock barrels and oil in place. So basically, when you calculate the A and H, is basically looking at the volume of the rock. BOI is basically formation volume factor. SWC is the saturation of the rock, and phi is God, I'm forgetting my Greek letters now. It's basically the porosity of the rock. So these are all factors that contribute to whether or not what's the oil in place in a reservoir. So before we extract this, what do they possibly use in terms of calculating? So we have pseudo-MCMC, like what I mentioned before. So you use a Markov chain. So basically, like you use a formula and you kind of create iterations, all the possible values based on the likelihoods for each of the different parameters that you see in the equation before. And it creates an estimate, and it's usually a distribution, somewhat of a distribution where you more or less get the maximum value, which is the mode. You also use reservoir simulations. Now, this you use packages like Eclipse or CMG, which are notoriously quite expensive. Or you use hybrids. So basically, you try to cut down the computational costs. So you probably use a hybrid model of using MCMC as well as some reservoir calculations, and that's going to be able to calculate the area, so to speak. Right. So, like, yeah, I mentioned this. So we use packages like Simulink, Eclipse, CMG. So those are all packages that we tend to use for programs that are generally quite computationally taxing. So how do we approach this now? So there are certain distributions when you're looking at petroleum risk that we look at. So we have uniform and triangular distributions. Now, let's say, for instance, you want to look at the saturation of rock, for instance. You know it's going to be between 0.1 and 0.4, but you don't have any idea what it will be. So you may actually use a uniform distribution. Now, when would you use a triangular distribution? Triangular distribution is basically now, I know it's between 0.1 and 0.4, but I think it may be closer to, let's say, 0.23. So it will have a peak to around 0.23. So it's sort of shift your distribution a little bit where you actually have a larger likelihood of being around 0.23 as opposed to, so the distribution shape tends to look more triangular as opposed to a uniform, where it's basically a flat line where it can be any value in between, and that's the training. Now, generally, that we tend to use triangular distribution when we do have some insight. So when you perform some certain amounts of well tests, then you would get that sort of information out of there. Other one is exponential. So we tend to use decay. When you're looking at a decay, we tend to use an exponential type of distribution. So that's another common distribution we use. And these distributions are usually somewhat easier to encode when you're looking at trying to make calculations. And of course, everyone use the Gaussian, the normal distribution. So we tend to use that a lot in a lot of applications. So and it's easy to integrate the normal distribution into your equation. So these are the common distributions that we look at when we're looking at petroleum risk. So let's dive a little bit in it. So why am I talking about this? So especially for startups, because I work for a startup as well as doing research and stuff, most of the time you have a limited budget. You have a limited budget in order to perform some of these calculations. So you may not have all of these things. So you have to be clever in the way that you approach these things. So you have to now explore CMG. We tend to use CMG a lot, but it's quite expensive and it takes a very, very long time to calculate the actual reservoir calculations based on different topologies and stuff on the actual site. And small and medium-sized enterprises, they basically they don't have that kind of resources to do that. So they now need to be a little bit clever. So you now need to try and use some maths behind it to see, like, can I now move away from this? Now, I know what they tend to use there, so maybe I could try to do this. And this is why I introduced Laplacian. Now, if you try to, and you look at, oh, but you can't use Laplacian for this because that is actually at the expectation of a Gaussian distribution where for a posterior. So you're basically looking at the maximum likelihood for the posterior distribution. But like I said, we're using a pseudo setting. So it's technically looking at the formula, and we did an expectation of that. So which is why it's still used. And we would see this in the example that I'm putting forward. Right? So I mentioned already, so you generate values based on the distribution given for the STOIIP. So they basically stop oil barrels in place. So it does not create a posterior distribution. So this is why some people might say, oh, but we can't use this, but you can. But you're actually looking at the likelihood value. Now, if you've been working in the petroleum sector for as many years as have you realized that a lot of these distributions tend to be unimodal. And what I mean by unimodal, it has one peak. So if it has one peak, what does that look like? When you're drawing a Gaussian curve, does it not look like a one peak distribution? So the whole idea behind Laplacian approximation is to now use something that's unimodal and force fit it to a Gaussian, which is what Laplacian basically is doing. So let's look at this distribution. So I now have a distribution that's now P, and I'm now force fitting the Gaussian, which is the green line. And you see the other one where it shows when you do your MCMC calculation there, you basically now try to force fit a Gaussian to that. All right, and it's basically used by creating a Hessian matrix, which in theory is, well, not in theory, it's actually the second partial derivative matrix, second order partial derivative matrix for, that's what a Hessian matrix is. And we force fit that now to look like Gaussian, and we get an approximation for that. So this is in that theory what I did, right? So I know I'm using a Laplacian. So what are my shortcomings? So unimodal. So in order to fit a Laplacian approximation, it needs to be a unimodal model. What I said, I mentioned this already. A unimodal model is basically a model that has one peak. So it's obviously it's easier if it's Gaussian, because if I'm force fitting Gaussian to a Gaussian, it's more or less a fit. So that's going to be nice. Variation methods for more global. So which is what we're doing is we're actually using a variation method for more global. So we're using the technique, but not actually using Laplacian approximations. So we're using more or less what's known as a framework, but not actually Laplacian. So variation methods are more global. So you tend to use those things for Laplacian, which is what we're doing now. And you have to understand, like, even when you look at any sort of setting, you look at what assumptions may be invalidated and how would you approach certain things. And this is one of the techniques that you need to go through when you're looking at any sort of computational method, how you go about validating your model, so to speak. All right. So now, this is a reservoir, an actual reservoir. Now, when you're looking at different, I only pulled the ones that use, so you see the distribution used for each of the different factors. So you have like area, you have thickness, you have porosity, you have water saturation, and the oil formation volume factor. And I use the distribution type for this MCMC algorithm. So when you do the MCMC algorithm for the distributions, which is technically like a priori. So this is why we say we still use a pseudo-MCMC, because basically you kind of have a distribution for each of the different variables of interest. And now, as you have that, it gives you now, I'm taking this. So let's see if I can put this into easier terms. So like, I know my area. So it has a curve, and this curve is following a normal, and the mean is around 1890, and your standard deviation is around 450. So you know 440, sorry. So you know for a fact that the area, most of your area would be within around 70-something% will be between one standard deviation of the mean, which is the 1890. So one standard deviation on the right side, don't ask me to calculate mass. You can all compute that. So 450 plus your 1890, you know that's around 70%. So when you're now running your simulation, you know that it's sort of, think of it like a Gibbs sampler where you're just not putting it in and you're putting it in the numbers in there, and it's falling. So you know that most of the time your numbers will be within one standard deviation. Like 70% of the time, and it puts that there. Your thickness as well, it's following that, and it's plugging in all these values. So it's likely that the thickness falling out, and it now plots those numbers. So that is what we actually did. So what this pseudo-MCMC do is now taking all the possible values of the area that will go in and the likelihoods for those, and it's plotting those now into that formula that you see in the very beginning of the slides. And that now plots somewhat of a distribution. And based on most of the times over time, well, we use mostly normal here. So you know for a fact that it should more or less follow a somewhat normal distribution. So it's easier to fit a normal distribution to that. But it doesn't have to be normal. You could actually put the other distributions in there, and you can change it. So you could put the triangle or the uniform, makes the computation a lot easier, for instance. So now, based on that, this is what was done for the MCMC calculation. And we have some results from here. So the expected oil in place is actually around 13 72 so million stock tank barrels. So that's what the pseudo-MCMC algorithm chunked out using, well, obviously if you use different distributions for your base for each of the variables, then you are going to have different estimates for your oil in place. But again, if we are absent of drill tests or absent of any taken log records or any more insight that would that would shed some light onto the uncertainty or what the possible range of values, you tend to be a little bit more you have a lot more variabilities that you try to be a little more sensitive in terms of calculating. And it plunks out these sort of values for you. So when you look at this is my MCMC algorithm, and you're looking at the chi-squared value and the chi-squared test, you basically know that's likelihood it's still between there. So you are now saying that it's quite likely that this is around the value that you're getting based on what you're seeing for this statistical test around of this. So I'm saying the MCMC algorithm was around 1372. So that's what we're going to be using to compare, because I'm comparing the Laplacian approximation to the MCMC algorithm. So now let's look at how we calculate this. So as I mentioned, the mean is 1372 and the actual oil in place is 440 million stock tank barrels. So that's way off. That's you overestimated. So the MCMC algorithm overestimated, and that happens a lot, which is why we need to be a little more, we have to use techniques when we're looking at things that we need to use techniques that would look at the sensitivity of each of these. So you now have to test on your model, if you change the value by a certain much, how much more sensitive it's going to be, so that I don't run into this sort of problem. So this is even one using the technology. So this was generated using Eclipse. So this is actually using one of the tools that they tend to use in in calculating this. And you realize you overestimate it by a lot. So you tend to put it, but that could be due to many factors. Like for instance, when we were looking at the Angostura well, and we did the reservoir calculations for that, they didn't take into account the geology was highly faulted. So you have a lot of pockets. So the actual oil in place was a lot smaller than what was given, and the capital demand for that was quite high in terms of being able to go ahead and drill the test. So we need to be a little bit more strategic when you're looking at things like that. And these are things that we need to look at when we are trying to calculate the oil in place, because you need to make sure and do sensitivity checks. So all of these, you don't run into overestimation. Well, at least you tend to overestimate sometimes, but at least be a little more strategic in when you're doing that. So now, this looks a little bit crazy, right? So look, I'm just going to walk through this a little bit closer, because it looks quite mathy, and I promised you it wasn't going to be mathy. So what is expectation? So expectation, you can think of expectation as the integral of x by the probability of x. So if you're doing statistics and you look at the expectations, whether it's discrete or it's continuous, you're basically using the expectation of x times x. Now, remember I said we're force fitting normal distributions. So if you look at that, on the first bit, you realize from the first part of the equation, which is the formula for the STOIIP. So that is the formulation you use to calculate the oil in place. And everything after that are all the normal distributions, considering the normal distributions, and we use normal distribution each time. So what does this look like to you? A formula times a probability. So the likelihood that occurred, and which we're using from a normal distribution. So technically, what I'm calculating here is an expectation. So it's an expectation of the formula. So it's not as you would normally introduce like a posterior distribution, but it is still an expectation. So it's easy to integrate, and it's very easy to integrate a normal into because there are lots of techniques that we could use to do that. But that's what we're doing. So now, if we look at, and I said I wasn't going to be math, so I didn't go through how we calculate the partial, the derivatives or anything like that. So using that equation there, I then now calculate what the oil and place with the same parameters. So if you look at, if I go back, if you look at the MCMC algorithm that they used there, and you see the different distributions with the mean and the standard deviation, I use that same information from there to put it back into this here as an operation when I started to optimize the equation, and I pulled out the value. So what I got was a mean of 853 million stock tank barrels. So, but remember, the actual oil that was in the reservoir was 440 million stock tank barrels. So it's overestimated as well. But if you look at the MCMC algorithm, you see it's 1372 as opposed to 440. The overestimation using the MCMC is much greater than with the Laplacian value, right? And like the same sort of statistics, you look at the chi-square test and what's the likelihood of that actually occurring. And the reason why we use chi-squared is because I'm using a chi-squared is when it's easier and you try to not work with the distribution. So it's a very good non-parametric approach when you're trying to test the statistical significance of something. So we tend to use chi-squared a lot because you don't need to have, it doesn't need to adhere to all the different assumptions. Like for instance, if you're dealing with a logistic regression, for instance. So if you're using logistic regression, you know that linear regression, you know you need to have constant variance. You know you need to have homoscedasticity, which is basically constant variance. You need to have non-collinearity. Those are all assumptions that you need to adhere to. But when we use the chi-squared, it's technically a non-parametric test. So we don't need to adhere to all of those assumptions. So it's easier to go by with someone looking at that. So that's why we tend to use chi-squared a lot, especially when it comes to biological substances as well. Chi-squared test is quite powerful. But you realize from the Laplacian approximation that it's smaller. So this is now showing, okay, Laplacian is less computationally taxing. I know it looks quite confusing, but when you're doing the whole approximation, you're now using, doing the approximation, the MCMC algorithm, what it does is compute and puts it on, you run through 1 million iterations. And when you run through 1 million iterations, by putting 1 million values of all the different possibilities, it plunks out the value that you see that you have from the MCMC algorithm. The Laplacian more or less does the same thing, but it's less computationally taxing than the MCMC algorithm because I'm now force-fitting it to a Gaussian that I know is easy to integrate out. And this actually provides a much better approximation to the oil that's actually in place. So this here is a technique that we can use, and I think we need to use it more and think outside the box when we need to find clever ways of trying to minimize costs, minimize things like computational taxation on anything, and you're able to see it. So understanding the procedures on how to modify perhaps assumptions is quite important. It's quite important. So now let's look at the sensitivity. So like I mentioned before, when you're looking at MCMC algorithms, you need to try to do a sensitivity test to see how the variation from any of the different parameters, the variables on there, how much your approximation is adjusted. Now, remember, I'm looking at the sensitivity of the mean now. The reason why we're looking at sensitivity of the mean is because we're now looking at the expectation value. And under the MCMC approach, and when I plugged in values, if you change the area by 1 unit, you have a sensitivity around 51%. So the area actually seriously affects that. So the large changes in the area can affect your outcome for the MCMC algorithm. But the sensitivity under the Laplacian approach is much lower, right? Likewise, if you look at all of these things here, it's telling you the sensitivity under the approach is, by much changing. So even though you're changing the approach, if I change the value by one of the units, each of the different parameters, it's changing it much smaller so that it doesn't affect the modeling approach when you're using the Gaussian. And that's because we force for the Gaussian. It helps a lot with that. So you realize that the sensitive analysis, it tends to be very highly sensitive to changes in the values. So you know for a fact that when you have high sensitivity, you're going to be overestimating or underestimating by a lot. So if we now say the area, like for instance, when I mentioned before, like when we looked at the Angostura field, they basically overestimated because the area that we were thinking of is actually much less. So the fact that when you put that into that model and you put that there, so if we had actually used Laplacian at that time, we might have actually realized that, okay, this would have been smaller, and you might have been able to know how to approach funding, or you would not, people will lose their jobs, so to speak, because if you predict that you're going to have this amount of oil and you have much less oil, then obviously you're going to now you're spending a lot of money to produce and do well tests and do thing tests, and then afterwards, in the end of the day, you don't have as much oil as you think you do. And that's usually a problem where we have a lot when you look at those things. So you need to have more robust techniques. And this is just to show you that this technique is actually a little more robust in terms of knowing how sensitive that you're looking at in terms of the parameters. So this is what I have under the sensitivity analysis. Right. So as I promised, it was not MATSI. So MCMC approach was overestimated, but much more than the Laplacian approximation. So those are the key takeaways. So I know for a fact that this approach can be used in calculating the oil in place. Now remember, these are preliminary results for algorithms. So these are what you normally calculate beforehand. So it helps to give an idea of how to go about, how to budget, how to do things. It's always better, as with anything else, it's always better when we have more data. So if we have more data, we can provide more accurate models and better estimates. But in the absence of this, we tend to use techniques that we use all the time and have information. Like for instance, if I looked at a well in a somewhat similar region, I know that the porosity of rock is usually around that if it's usually the same type of formation, but or not. So this is what you generally have to do. So this is what I had to present on Laplacian approximations, and I believe they would share the slides with the participants. You can have a look at where I pull the reservoir, because I use the public reservoir, and you can even look at what we use. And I think there's a PetroSkills gives a nice course if you want to get into how we calculate petroleum risk and decision analysis. It gives you an idea of the type of distributions and some of the things that I've mentioned. They would do the same thing. So this is what I have presented, and that's me. Now, usually when people have to present maths, people tend not to ask questions, but I hope I sparked your enthusiasm to perhaps ask me something. So shall we open the floor?
Congratulations for a beautiful presentation.
Thank you, thank you. So do we have any questions?
No, just a comment. Just a comment. Let's hope that we can all work together into having projects, and I really suggest applying for grants, for research grants.
Yes. Well, I'm actually currently working with, so one of the projects I'm involved in right now is using AI to try and build a better learning algorithm to calculate the economy. So we're using we're trying to use more sustainable energy now. So that is getting from solar. But these energy communities have batteries. So everyone have these batteries, and they now sell the energy back into a community, and they usually have a figurehead that. So now I'm creating an optimization algorithm to basically try to maximize that so we can actually have better sustainability. So this is now some of the text that we looked at. So that's what we're in. So yeah, that's actually one of the functions with the FCT. So the institution in Portugal is the FCT.
That's great. Congratulations. That's wonderful. Did you publish that?
It's I think in the process of getting the paper published. So it's one of the works that I'm working on getting published.
Dear Professor, thank you very much. Now, that was a great presentation. I think there's a question from dear Sebastian. Ask, please. Yeah, Mr.
Can you hear me?
I can hear you now.
Sebastian, okay, so you can ask him.
All right. Thank you
Yes,
so
yes,
much.
yes.
I love the way you use the Laplacian operator in drilling
Yes.
that. I'm finding it, I mean, as at yesterday, I was trying to use Laplacian transformation in extracting piezo. What are the challenges that you face? Because I seem not to get my output correctly. What are the challenges you face when you are trying to fit into that model?
Okay, so it's usually not. Can I ask what platform you are using? Python or what are you using?
I'm using Python
or
at the
MATLAB?
moment.
Okay.
I'm using...
All right. Are you working in a university setting?
No, it's just a personal project for piezo operation.
Okay, so I think if you want to look at Laplacian approximation, now usually problems arise if you don't understand how to create a Hessian matrix. So I would suggest there are ones, I've not used it in Python, but there is free packages that around, you can reach out to me after. I think my email address is anything, and I can guide you as to where you can probably get some help in using a Laplacian approach. And also perhaps I can give you some insight how to proceed in terms of knowing how to convert any particular sort of maths, because that's my strong suit, maths, into the things. I'm not a huge fan of Python for machine learning too much, because it's especially for statistical modeling. It can be done, but a lot of times I have to build my own units in between. So which is the problem that you have with Python a lot. You tend to have issues around that having to create it, but there are packages, for instance, like in R, but this was done in MATLAB. So it's a service that you actually pay for, only because a lot of the partial derivatives packages are a lot easier to code it with in MATLAB. But coding in MATLAB is quite similar to Python. So some of the syntax is almost identical. But you can reach out and I can show you how to go proceed with some of those things. But the challenges is usually, once you know how to formulate your equations, it's usually straightforward from there. So making sure you put the integration aspect of it okay.